So these are all the people involved. ACAP, the Alaska Center for Climate Assessment Policies, will be working next year. It's really a great place, and so they put a lot of effort into the Alaska part of this presentation. So that's me in Alaska. Kira did a great job going over that, so I need to. So I'm going to start by going over the work that I did in my thesis, which I just defended on Monday. So hopefully there's no big errors in it, because that means my committee didn't catch them. But, so I'll go over that. That's a picture of Great Basin National Park at Stell Lake, the top, the higher elevations area, but we're going to be looking a little bit lower for since just a second. So there's a lot of different ways you can try and reconstruct paleo fire history, but one of the most common ways has been to look at charcoal preserved in lake cores. Unfortunately, there's not many good lakes to preserve charcoal within the Great Basin of the Western U.S. So what we've done here is we've taken sediment cores from wetland meadows that are kind of seasonally inundated with water lower in the park, and we've used those to try and extrapolate fire history. And it's a really interesting area to do this kind of research because there's been a lot of fire activity in the area, but if you look at the National Charcoal Database, you'll see there's a big hole over the Great Basin. There's been a one-hole study done in the Central Great Basin on fire history. And then there's been more studies done on either end in the Rockies and in the Sierra Nevada. So it's a really interesting area to take a look at this type of information because it hasn't been done there before. So that was our goal with this project, was to use charcoal to model Holocene fire activity in Great Basin National Park. So we extracted several cores. Two of them were extracted, and one in 2014, one in 2015 in an area called Dead Lake Meadow. Meadow looks like this. It's a really, has a river running through it, really kind of wetland meadow with forests surrounding it. And we cored using a Livingston core, which is usually made for lake cores, but it was modified for this purpose. In 2018, they returned to the meadow, a different meadow in the park, and they used a new coring mechanism that Jim DeGrand over in geography developed. And it's really an amazing thing. They have this, you can't see it back there, but there's a disc they put on this pipe, and they attach it, and then everybody stands on it / kind of jumps on it, and it depresses into the ground and creates a much more continuous core. They had problems with the Livingston core. There's all these gravel lenses, which we'll see in a second, that broke up the core a lot. This creates a really great smooth profile. And then they extract it using this. So Forrest has had the great experience of jumping on the coring mechanism, but it's a really, really fun thing. So the analysis for these haven't quite been done yet, so they're not in this analysis here, but Jillian and several other people in geography have been working on those. So it's been really great work to see those slowly get done. So these are the different coring sites within Great Basin National Park. This is Wheeler Peak, the highest part in Great Basin. So where Forrest does a lot of his work. Dead Lake Meadow is down here. This is the one site called South Fork Baker, which really looks great, and that's what we've been counting this semester. And then Strawberry Creek is up here, which is where that one picture is from. So this is a picture of the 2015 core, which is what most of my research on my thesis is based on. It's kind of hard to see, but basically the top of the core is really organic rich up here. It's kind of hard to interpret. And then there's all this sandy kind of gravelly material here. And at the bottom, it gets really gravelly again and isn't all that great for an interpretation. Probably the river meandered over it several times. But the center part of the core is nice and continuous, and you can actually get nice layering throughout it. So that's where we spent most of our time doing this analysis, was in that center part of the core. So there's basically, you sieve charcoal and you do a process to make it show up under a microscope a lot better. And this is what it looks like under a microscope. You can count charcoal grains. They're not quite easy to see, but there's a charcoal grain. There's one, there's one, there's one, there's one. This one actually is quite a lot of them. And in this area, they're mostly intermixed with quartz and biotite. Biotite actually looks a lot like charcoal underneath a microscope like this. So you need to take special care to do that. But my double major in geology really helped me with that. So these are the results from our 2014 test core and our 2015 core. And you can see this is just the pure charcoal counts at the different sieve sizes. You see this really interesting behavior, and we'll explore this a little bit more when it's extrapolated using an age model. But this break kind of, and it's kind of represented there in 2015, kind of jumps out right away. So we use carbon dating for this. We carbon dated the charcoal itself, which is a little bit problematic because the charcoal carbon dating is older than the actual deposition, but this the real closest that we got to. And so here's a basic age model. We can see the top of the core is a mess. There's this age reversal, and we don't really understand what's going on with that. So basically, I didn't analyze the top of the core. I focused on this middle section where we can actually have a nice continuous age section to work with. So using the chart analysis software, and I'll actually go to the next slide to show this, you can extrapolate with your age model the charcoal accumulation rate over time, which is a really easy way to look at this type of analysis. And so what you can see in both 2014 and 2015, there's some higher fire activity earlier in the core, around 8,000 years, and then there's this jump to a much more active fire regime. Now, the timing is problematic with this. As you can see, this jump happens about 5,800 years in the 2015 core, but it happens significantly earlier in the 2014 core, around 6,300 years ago. It's a pretty big jump. I would hypothesize that these are the same event. They last about the same amount of time, and they have this very distinctive shape. But the timing is a little bit problematic. But 2014's age model is a lot less robust. It only has 2 dates rather than 12, and it has more gravel lenses in it. The core is broken up more. So I focus mostly on 2015 as a much more continuous record, but that timing is something that should be addressed with some further research. So I want to link charcoal to other studies that have been done in the area. What we can do is we can look at a Speleothem record, which was just done in 2015 in Lehman Caves within the park. It's a really interesting record. And the overall analysis from this record found that they used magnesium, I think it's, I don't know, magnesium and calcium, I believe, ratios to determine precipitation within the park. And they also used other things like lake levels from other studies within the park. And they saw this drying trend initiating about 8,200 years ago, and then reaching a peak dryness, I guess if you want to describe it that way, about 5,800 years ago. Interesting to point out, right when we have that giant shift in our fire activity 5,800 years ago, we have this huge, or relatively large, anomaly in the carbon isotopes in Speleothems, much lighter isotopes. They don't interpret that all in their study. They just kind of mention that it's there. I don't know how to interpret it, but I would propose that it has something to do with the change in fire activity at that time. I think they're linked in somehow, but I don't know how. That's another area of future research to look into. Also looking at research that's been done here by Dr. Reinman for his thesis on Chrionomids preserved in sediment cores. What we can see is that looking at that analysis, warming really began in the park 5,800 years ago, and you saw peak in temperatures about 5,500 years ago within the park. That aligns really well with our charcoal analysis. And just looking at the basin as a whole, 2015 study by Wall did a really great overview of paleo records within Great Basin. And what's interesting to note is that things are a little bit more consistent in recent time. You know, paleo records agree. Paleo records do not agree 5,800 years ago. Geographically, where you were in the park really changes what your record is saying. And that's why I decided to really focus on paleo records that were done close by. This is probably related. They mentioned over here, there's a lot of modeling that tries to go into the North American monsoon at this time. And the monsoon is very variable within the Great Basin at this time. It's likely contributing to this variability. But there's some thought that unlike most of the basin, which appears to be wetter and cooler, that the eastern Great Basin where we are is further east from the monsoon. So it remains drier and warmer. But that's very much an area of ongoing research, and that monsoon is not very well constrained at all during that time period. So just some conclusions from this. There was definitely some environmental shift 5,800 years ago that greatly increased the rate of fire. That I think is pretty certain from this analysis. I would propose that fire is more sensitive to temperature than to drying alone, because the environment had been drying for a long time before it started to warm, at least going by the timing of these two studies. So it's really this start to increase in temperature that seems to increase the fire activity. So drying may prepare the vegetation, but there's some temperature dependence that you need to really initiate that regime shift. And finally, to really further this analysis, the number one thing we need is a pollen analysis. There's no nearby pollen analysis, particularly done within the forests of the park. And that's really important to understanding the vegetation regime of this area. That's really what we need to understand this more, is a pollen analysis. But I would propose, you notice that the fire activity drops while the environment continues to warm. The vegetation probably changed quite dramatically in response to those fires. And a pollen analysis would really help us better understand that. So any questions on that first half? Because I'm about to very dramatically shift to a very different topic.
In terms of the temperature being in effect, could lightning strike be possible?
Absolutely. That's something that would be related to the monsoon. Is another big control on fire is ignition source. And so that's often more precipitation can actually mean more fire by ignition sources. The monsoon complicates that. The monsoon is so seasonal, and especially if we're near the edge of it, there could be many events where the monsoon could be in the area, but the convection is elevated. So there may not be any precipitation reaching the surface, but there could be lightning. And that's really something we can't know from paleo records alone. So.
But are ignition sources important in controlling fire at the time scales that you're looking at?
Absolutely, but I don't know. Yeah, I would say for sure, because the desert is, well, it's not really a desert so much. It's very likely that it could be ignition limited because they have so few occurrence of thunderstorms. The rate of which ignition happens can be relatively low. So for example, this is a big problem with fire in Alaska. Just to relate it to that is many times the vegetation is prepped for fire, but there is no ignition source. So there are several years where the climate could have generated a large fire, but there is no ignition source to cause it. So I understand what you're saying, saying that maybe over time that effect would be washed out. That might be a more year-to-year variability. Yeah, I would need to honestly look at more work about long-term influences of ignition on fire.
So 5,800 years ago, there was like this shift in the climate.
Mm-hmm.
Were you able to check what was the vegetation cover before and after the time? Is it similar to what it is right now? That's
again really why I think a pollen analysis would greatly benefit this analysis, because we really don't know what the vegetation was at that time. The Speleothem record goes into a little bit of discussion because they talk about carbon changes, C4 versus C3 plants, but they say that at least over Lehman Caves, which is at a significantly lower elevation than these cores, that the vegetation's been relatively constant. More of this kind of alder-ish shrubby environment. So vegetation, I would bet would almost certainly change, but we need to see other records to tell us how it changed or in what way. But leading up to this event, there were definitely wetter times in the environment. So wetter than today, before it started to dry. So probably had influence in building up vegetation. That's cool. Any other Great Basin questions? All right. I've tried to stall enough for Brian, but can't stall anymore. So let's start talking about fire in Alaska. I'll probably skip over a good chunk of this, but I wanted to give a broad overview of what Alaska is a little bit in fire in the Arctic and Alaska before I go into my specific research. So probably the first thing to note is Alaska is really big. This distance is about 600 miles. To give a perspective, if Ohio fit into Alaska, it'd be like there. So it's a very large state, and it's very, very heavily controlled by elevation. So there are 3 major mountain ranges in Alaska. There's the Brooks Range in the north, the Alaska Range in the south with a whole bunch of smaller ones, and then there's the White Mountains or the Tanana Uplands in the interior. And the boreal forest kind of merges all around that, but mainly in the interior between the two major mountain ranges. I look mainly at the tundra, but we'll look at the tundra in just a second. So just to give an idea of how elevationally controlled the boreal biogeography is, this is just a great kind of famous diagram that shows on south-facing slopes, you get black spruce. On north-facing, sorry, I reversed that. On north-facing slopes, you get permafrost and black spruce. On south-facing slopes, you get more mixed vegetation with deciduous trees that aren't as burnable. And that's an important distinction. And then in the lowlands, it all depends on where permafrost is. You know, is permafrost allowing water to drain with more permeable sediment? Then you get deciduous trees. Is permafrost in more low, dusty sediment? Then you get conifer trees. Or you have a big, thick peat layer, then you get more grasses. So it's really strongly controlled by hydrology and permafrost, along with elevation. So it's really interesting to note. And just to show you how incredibly rapidly vegetation can shift in Alaska, here's the Yukon. You can see all these black spruce stands with some conifers and alder, looks like areas mixed in. And you have this large area where it's deciduous trees with alder in the middle here. And it just rapidly changes. And it's almost certainly connected to permafrost in that sense. So very different controls. And this is a great picture. You have a mixed spruce deciduous on the south slope. And as soon as you cross to the north side of the slope, it's all spruce on the north side of the slope. So it's really unique controls in the Arctic that you don't get here. Looking at fire more broadly, these are all the fires that have occurred since 1940 within the interior. It's really an incredibly large part of the ecosystem. About half the area of the interior Alaska boreal forest is burned in the past 80 years. And that's about what you'd expect. Fires return there every 80 to 100 years. So that's a natural fire regime for the most part. 99% of the area is caused by natural fire. Just recalling how big it is. Some of these are incredibly large. And it's really important to boreal succession. Boreal forest probably is the best example of ecological succession in the world. It's relatively straightforward. Very few places in the world have such straightforward succession. So this is a stand that burned probably about 60 years ago. But you can still see, it's really hard to see, but there are some burnt spruce trees still standing there. But deciduous trees have grown up all around it. In another 40 years, under a natural regime, this would become a spruce stand. This is about 5 years after a fire. You have standing spruce and fireweed, which blooms all over them. So it's really almost an incredibly regimented system of the ecology in Alaska. And fire suppression is a big deal there. These are all the agencies involved in fire suppression. It's so complicated to manage them all that there's a whole other agency to manage the other agencies. It's a mess. But this is a map just as an example of the different fire suppression priority zones in Alaska. There's critical priority, which are tiny red areas. Those are basically all your towns in Alaska. That's about it. Then you have orange. Well, there's a whole other category in there you can't see, but orange is priority. So mainly along river corridors where there's a lot of cabins or places of natural resource interest, or the pipeline. It's really narrow, so you can't see it, but the pipeline is all orange. And then you have yellow, which is modified, which is mainly wildlife habitat or native areas of native importance that are protected. And then you have something that's really unique, a zone that does not exist in the lower 48. This is limited, which is basically no protection. They do not manage fire in those areas unless it's very dangerous to a specific aspect. So Alaska is probably the only place currently in the United States where there's a fully natural, in many ways, fire regime. So now I have to talk about fire in the tundra, which you probably noticed I didn't talk about very much because it's not relatively a large area that burns, but it's an area that's rapidly increasing and of rapid interest. So about 4.5 million acres of Alaska tundra have burned in the past 50 years. That's small by Alaska standards. They're very rapidly growing and difficult to forecast, and they influence a lot of local communities because a lot of communities, particularly in Southwest Alaska, live in the tundra, more so than the boreal forest. So they are perhaps more impactful, even though they're not as common. And they're traditionally modeled as grass and shrub fuels from the lower 48. So basically, heavily weight wind is the most important variable to modeling these fires in traditional fire weather modeling. That said, oh, I should point out that threshold for wind is about 35 miles per hour. They say wind growth grows linearly with, fire growth grows linearly with wind speed up to about 35 miles per hour in current models. Keep that in mind. Okay, so the thing is, no one's actually really tested this. No one's actually looked at tundra fire behavior on its own. It's mainly been in the context of these other models. So that's what we did. This was kind of at the bequest of the Alaska Fire Service. Forecasters there said basically fire was not behaving how they thought it would given traditional modeling interpretation. So that's what they wanted us to look at. So we looked at four major tundra zones in Alaska. Sorry, there's 5 there. The North Slope, the Bristol Bay area, the Yukon-Kuskokwim River Delta, the Seward Peninsula, adding the Selkirk River Basin, and the Noatak River Basin. Those are all the main tundra areas in Alaska. We didn't look at alpine tundra. We mainly looked at these 3 due to data availability. There is not enough, fires are big in the North Slope, they're getting bigger, but there's not enough weather data to accurately model them. There's not enough fires in Bristol Bay, though. That might change in the future. So the Alaska Fire Service wanted us to focus on what they called large initial growth days. They wanted us to tell them a fire might start in the tundra and burn for 2 weeks, but it won't grow beyond a few dozen acres. They want to know what is the weather like on that day that it grows and starts to accelerate exponentially. And so those are the days we identified. So to give you an idea of how many fire days exist or how many acres are burned every year in the tundra, you can see that the past decade has been quite active, particularly in Southwest Alaska. The vast majority of tundra, more than half of the area that's ever burned in Southwest Alaska, has burned in the past 20 years. So it's really an incredible time period there. There is one period here on the Seward Peninsula in 1978, which is just crazy, burned over 1 million acres, but we don't have data to look at that, so we didn't. These are just determining the fire growth days. All of them fell between May 24th and August 20th, so very much in the middle of the summer. We had to obtain reliable weather data. That was our next step now that we had the days that we identified. Cool snow squall on the North Slope. So we used mirror reanalysis data. The reason being there's been work done there at the University of Alaska that showed that for tundra regions, mirror was the best reanalysis data set for weather variables. That said, I would love to redo this using the Arctic reanalysis done here, but I actually didn't know that existed when I was there. So, but mirror performs relatively well. Also looked at the station data that does exist. There's practically no stations in these interior zones. There's a lot of coastal stations in the tundra. They're in a marine layer and they're not going to give us good information for these interior tundra fires. So there's very, very few stations that even have a 20-year record in the tundra. So we can only really pull one for each region. For the Seward, there's literally not a single station in interior Seward that has a continuous record more than the past 20 years. So I had to cobble together 2 different stations, which is boggles my mind, the lack of data. So what I did is I validated mirror against some of these station data to just verify very roughly that they had good agreement, and they did. So these are daily average temperatures over a climatology of that about 20 years that we identified since 2001. And daily average wind speed, which I wanted to make sure at least had some significance. So there's a lot of variance. There's a lot of local effect almost certainly going on here, particularly in the Seward. But synoptically speaking, on the large scale, mirror performs pretty well. So we decided to go forward with it. And so we wanted to look at the large variables that they were interested in seeing, which was wind speed, humidity, temperature. Those are the 3 main weather controls. So we decided to look at all of them. We were hypothesized that these are wind-driven fires that require low humidity below 30%. So going forward, that was what we wanted to test. Did this independent, I'm going to show Mira data, but did this with Mira and station data, found the same results. So a lot of graphs that look like these. I'll probably blow through these pretty quick. But what you'll see here is 2 box plots for 2 different data sets, the climatology since 2001 and the fire days. I should say the summer climatology, that summer we defined. Summer climatology, and then the fire days that we identified, those rapid growth days. And what we can see is that on each of these days, the daily average temperature and the daily maximum temperature are well above average. Not too surprising. Yes, I'm using Fahrenheit because this presentation was given to the fire service. Sorry.
You are forgiven.
Relative humidity, you can see that significantly lower. This is not as low as current forecast guidelines would think it would be, closer to 30%, but it is significantly lower than climatology. Wind speed is where things get really interesting. So wind speed was not significantly different for fire days versus climatology. This is kind of high on average in miles per hour. 15 miles per hour for daily maximum wind speed, it's kind of high. But it's far below that sensitivity that models have up to 35. So if there is a wind signal, we should be seeing it at the synoptic level. Again, looking at the large scale, we're not modeling small scale stuff here. And I would hypothesize this is looking at basically for cloud cover and from radiometer sensors on the weather stations. These days are very, very sunny. So those temperature and humidity are almost certainly driven by sun, not by advection. So some conclusions from that. Overall, very sensitive to temperature and humidity, maybe not so much to wind. So I also wanted to look at a synoptic analysis. Does it make sense when you actually plot this on a larger scale? You can look at variables, but it doesn't matter if the synoptics don't make any sense. So I also created composite maps for these days over Alaska using mirror reanalysis. And you can see 2 meter temperature, just a sanity check. It is indeed tracking over each individual region as an anomaly every day. So warmer than average, great to see. Sea level pressure, see this weak, low pressure that seems to form over the interior during all these days, maybe indicating a heat low, maybe. But the big takeaway from this is there is no consistent pressure pattern that is bringing strong winds to this area. 500 millibar height shows the same thing, a weak ridge that centers over each area for its time period, indicating sunny weather, weak synoptic flow. So some conclusions from this: well above average temperatures, weak ridge. This pattern is consistent with a solar heating driving this fire. A note about mixing. I kind of kept this in there for the fire service folks, but basically you can occasionally in a lot of these events see low level dry air that inserts itself above the fire, maybe mixing down in daytime convection. That's a whole hypothesis that needs to be tested elsewhere, but it's a cool idea. I also wanted to make it as applicable as possible to the Alaska Fire Service. So I looked at fire weather indexes, and these are the main indexes they use for fire weather forecasting in Alaska. FMC, which is a short-term drying index, ISI, which is a wind-based spread index, and BUI, which is a drought-based index. Made very similar graphs. They're the same thing. Large fire is the same data set we were looking at earlier, those large initial growth days. Fire, I added as extra, is any day where fire grew in the tundra at all. It doesn't matter if it grew a little bit or a lot. And then the climatology. As we can see, FMC does a really good job at discriminating not just from fire in most circumstances, but from large fire. So FMC is a well-performing index in this case. Initial spread index, the wind-based index, again, a good sanity check, doesn't seem to be indicating anything. And daily buildup index, which is a drought-based index, it's higher, but it's not discriminating those days very well. To note, most of the fire parameters in Alaska are not having a high risk into 100 to 110. You almost never get that dry in the tundra at all. In fact, in the YK Delta, you never get that dry. So these are short-term drying events. You are not having drought behavior in the tundra that generates these. They are burning wet. And in fact, you can talk to firefighters who fight fires knee-deep in water. So you don't need drought conditions to get these. In fact, you only need probably a couple weeks of drought to get a BUI that high. So overall, FMC has high scale, ISI has low scale, BUI has some scale. So short-term drying is dominant here, as shown in the indexes. It's really important because ISI is currently the highest rated index for tundra fire forecasting in Alaska. So some overall conclusions from that. If you want to forecast, look at cloud cover, focus on FMC, and we're looking at mostly weak synoptic flow here. Most important word is synoptic. We do not have the data validity at all to look at the small scale, like plume dynamics of these fires. There's almost certainly a wind influence there, but on the large scale wind patterns are not important, as important at least. Future research, redo this with Arctic reanalysis. Honestly, I really want to see the results, but I have a feeling they'd be very similar. And you could apply this to many other tundra areas to see if this is a consistent result. And talking with researchers here at OSU that have done similar vegetation analysis in Scotland, it appears to be. So interesting to see. And I also just wanted to put in just a few slides, zooming back out to some climate change impact on fire in Alaska. Looking at a paleo-perspective, fire has changed quite radically in Alaska with the vegetation regime. So this is a really great paper on paleo fire, a paired pollen charcoal analysis done by Philip Higuera that showed when Alaska was a shrubby tundra, which is likely what the tundra is becoming shrubbier in Alaska, fire activity was elevated. When it was a grassier tundra, not so much. And then as soon as you had a deciduous forest type environment under the Holocene thermal maximum, wasn't so active in fire. As soon as you get spruce come in though, very active fire in central Alaska. Shows a little bit of variation through time. And this was done on the foothills of the Brooks Range, which has had a large variation in environment over time. It's a good place to do this study. But climate is changing really fast in Alaska, as probably everybody in this room knows. Sea ice goes down pretty amazingly every year. Winter temperatures are increasing by about 0.6 degrees C every decade right now in Alaska at current rates. So it's pretty incredible rate of change. Almost every month, something like 2/5 of the months in the past 5 years have been in the 90th percentile. Something incredible. And just last March, almost every single weather station in Alaska reported their warmest March last month, which is an incredible uniformity for such a large area. So very rapid change. And Alaska fires seem to be changing too. Not quite as clear a signal though. Of the top 5 years, three of them have been in the past 20 years. And the number of large fires, which isn't shown here, the number of large fires is certainly increasing. But the overall acreage burned, maybe not so much. But that might change, we'll see. What will almost certainly change is the vegetation regime, and this is ushered by fire. As fire takes down spruce stands, as it normally does, many of those spruce stands seem to be replaced by deciduous trees. And we can see a rapid modeled drop, as well as an observed drop up to that point in the number of conifer trees in interior Alaska. So it's likely, and modeled here, at least by this study, that we'll have a burst of a few decades of very intense fire in interior Alaska, replaced by deciduous trees and then a leveling off to a lower fire regime. And just to wrap back around to tundra, this is a great study that models fire return intervals using temperature and humidity and other model variables for central Alaska. Super important to notice, this does not have a vegetation model coupled to it. So keep that in mind. But under this scenario, under the warming to the highest RCP, we see incredible changes in the Alaska fire regime. So on the track we are now, by the end of the century, we could see 4 times as much fire in the tundra modeled under this scenario, using just temperature, which is, as we've seen, probably one of the strongest controls on tundra fire. So from a behavior perspective and from a long-term perspective, if you look into the literature elsewhere. So climate change is having a drastic effect. And even in the interior, at least before we get deciduous change to deciduous forests, likely to see about a doubling in fire. So really interesting stuff. So thank you to all these wonderful people who gave me money and who have helped me so much, both at the OSU and Alaska. They're all great people. Here are way too many citations, if you want them. Okay, you survived.
72%, the latter part of your presentation on the Alaska fires, did you present that to some of the agencies?
The climate change part wasn't in there. I mainly stuck to the fire behavior, but this is very much a topic of discussion at the Alaska Fire Service and other agencies. They're very much aware of this research. And in fact, I think Adam Young, who did this study, actually gave a talk there at the Fire Service. So they're very much aware and they're very much concerned. And there's a lot of questioning, actually. There's this idea based on paleo stuff that fire will decrease with a new deciduous regime in a warmer environment. The problem is, under current warming, we're going to blow past where it was in the Holocene thermal maximum. In fact, parts of Alaska probably already have. And the question is, yes, under this regime, deciduous forest was less burnable. But under an even warmer regime than we saw then, with different precipitation patterns, could it actually be more burnable because it grows faster? So that's what the Fire Service really wants to get a handle on, is the deciduous forest really going to be less, or could it actually be more? And that is very much an active area of research, and that question isn't settled at all.
When you look at more temperate environments, deciduous trees burn more or less than the...
They would, see, it depends on where you're looking. It really depends on the precipitation, and that's why the precipitation is such a big question. Alaska is very dry, relatively. You know, they get maybe a fourth in the interior of the precipitation we do every year, but there's so much permafrost, it doesn't really drain. But if you were to increase the temperature, change the vegetation, but not change that precipitation very much, which would be difficult to do given their topography, could you get a more active regime? And you do have deciduous forests that burn more in the western United States. So we don't know. It's an active area of research.
This sort of stems off of this discussion of like deciduous forests and whatnot. I'm more familiar with Kenai Peninsula, so it's has applied inland, but I know that the beetle infestations have led to a loss of evergreen stands, which has boosted deciduous growth or promoted a transition to grassland, both of which would affect fire regimes. I was wondering if you could comment on that transition.
Yeah,
relationship.
so the Kenai specifically has had a lot of bark beetle infestation, and the Kenai had some very large fires in both 2004 and 2015. The Kenai is interesting. It's kind of an isolated boreal forest habitat surrounded by the Alaska Range. So. Yeah, so addressing the beetle part first, there's a lot of debate in the Alaska Fire Service about the relative impact of bark beetle on fire behavior or not. Some fire managers swear by the fact that bark beetle makes fires more violent by creating more crowning behavior, what you call crowning behavior, that spreads between trees. Other forest managers think on the long term that bark beetle actually decreases fire activity by creating fires more frequently and making them less intense. I haven't really, I've seen some studies about this in the western United States, and different authors come to different conclusions. So what perspective you want to take on the bark beetle on fire, I think is a little bit up for debate. But it does certainly, especially in an environment like this, help facilitate a vegetation change to deciduous forest, and in some cases to grasslands, particularly in the northern wetter areas.
Do you expect to be able to continue to move with changing climate patterns?
Oh, the bark beetle?
And affect a wider...
Yeah, so the bark beetle has been infested in the Kenai for some time. It has so far not really seemed to make it to the interior. Exactly why? It could be because the interior has significantly colder. And when comparing to the Kenai, that probably won't change because the interior is a significantly different environment than the Kenai with ocean influence. If we were to have significant warming, that it might be able to go up, probably transported by humans because the Alaska Range serves as quite a biogeographic barrier to it. But humans have done that before, so I'm sure that they would do it again.
What's the role of lightning in these fires?
Yeah, so the vast majority of these fires are caused by lightning. So lightning is the ignition source. And in many cases, lightning is a strong inhibitor, the lack of lightning is a strong inhibitor in fire in Alaska. So there's a lot of studies that talk about the tundra as a lightning limited regime, because there are many times when the environment is primed for fire, but lightning doesn't set it. And so you can see this in some of the paleo records. For example, this one doesn't show it so much, probably because there's always been sufficient lightning at around the fire return interval. But down here near Wrangell, St. Elias, there have been analyses that show that during wetter periods, there's more fire activity because there's more lightning and more. So the specific role of lightning seems to be dependent on your specific location. So it's hard to understand, I think. But in the tundra, I would say in the tundra, lightning plays perhaps an even more important role because convection is even rarer in the tundra, and it is perhaps more than anywhere in Alaska, especially the North Slope, becoming more common.
Frequency is increasing for lightning.
Yes, lightning is actually one of the strongest indicators of climate change in Alaska, you could argue. The Alaska Fire Service has done a great job tracking lightning in the state over the past 20 years or so. And even in that time period, at least the researchers I've talked to there are convinced that lightning is increasing with climate change. And it's really impactful on the North Slope. The North Slope environment is, I didn't touch on very much, but is a big question of fire-prone behavior. And there's many of you probably heard of the Anatuvik fire that happened here there several years ago, a very large tundra fire. But I think these principles, even though I didn't look at the North Slope because there's like no data, no, the fire service didn't start collecting data there until the Anatuvik fire because they didn't think it could burn. I think a lot of this would still apply up there.
Is that an input to the models for predicting the future?
For lightning, for the most part, especially for the model I showed, no. This model, very basic. I think they just input like a lightning percentage, but it's not modeled directly in any way. So it is, but actually coupling it, they're really attempting to do that at Alaska. There's been a lot of difficulty with that. It's a real challenge to try and directly model that.
I was curious, you mentioned that firefighters fighting fire in extremely wet conditions. So what's happening there with the system, permafrost, tree canopy, that you're getting that kind of conditions? You'd expect, it just seems very different than.
Yeah, let me jump way back. Show you some good examples of what I'm talking about. This is actually a good example. So this is an example of some fires that occur in Southwest Alaska. Southwest is really, really wet. It's essentially a giant outwash basin with river deltas flowing through it. Pretty flat, very, very wet. And this is a great example of how wet it is. There's lakes all over the place. Partially held by permafrost. It's preventing water from draining. It's some of the wettest areas of Alaska. They get a lot of rain near the coast. So there's a lot of influences, and there's a lot of rivers that flow through it. And the vegetation there, it doesn't, I think it's their evolution to that colder environment. They're not always uptaking all the water they're immersed in because they're immersed in it all the time. So they can still dry out even if they're in water. So you can see videos and stuff of firefighters fighting in these lakes, and the fire will burn the vegetation growing in the lake, burn right over it. And the other thing I would mention is that I don't particularly know how that works. That's almost more of a fire ecology question. I'm not that attuned to it. But I'd also say is that the hydrology is super local. So this could be really wet, but what could be in here could be really dry, just because the permafrost may have melted in that interior and the water can drain out below. So I'd also mention that the hydrology is super local, and to understand specific fire behavior, you do need some hydrologic understanding. So when you get down to the scale of a single fire, that becomes really important. But yeah, it's crazy.
What's the think about fire in Alaska? Are you thinking about, do they talk about the CO2 emissions coming from these fires, or is the carbon balance in any way being part of the discussion?
So carbon balance is a discussion. There's a lot of, looking at broad scale boreal fire, there is evidence that should fire increase how it's currently anticipated to, that the boreal forest will become perhaps a source of carbon rather than a sink. Its efficiency as a sink will certainly decrease. So it's somewhat of a feedback. The absolute magnitude of that, I don't have numbers off the top of my head, but it's not unsubstantial, but in comparison to human emissions, quite small. Tundra is an interesting question. There is an incredible amount of carbon locked in the tundra. And when you have these fires, they usually burn through what's called the duff layer. And they can burn, if they're intense, burn very, very deep, feet into the surface. And that can release an incredible amount of fire. There was modeling done at the Anatuvik fire that showed an incredible amount of carbon. It released more carbon than the whole boreal forest uptook in a year. So they are incredible carbon sinks. That was kind of, got the idea, kind of an apocalyptic paper when it came out. they've since had a paper after that that said, over the past 10 years of growing in the Anatubic fire scar, it's uptook almost all the carbon it released. So at least at the current rate of tundra fire burning, it's probably not much of a source. But should fire become significantly more common, and should microbial activity and things increase in that currently frozen soil, it could become much more of a carbon source. Specifically, how much I know is another very active area of research. It's not very well understood, but it's definitely in the realm of possibility.
So you're heading to Alaska.
Yeah.
And what will you be doing?
So I will be working at the Alaska Center for Climate Assessment and Policy. So I'm really interested in kind of what I did with this very applied research, working for the Fire Service to create a specific piece of climate information for them. So that's really what I'm interested in. I'm also interested in some of the climate communication stuff. ACAP there does a lot of great work, outreach in the state of Alaska. So they're what's called a NOAA RESA institution, so it's kind of their overarching mission. So that's really what I'm interested in. I was really excited that I actually got funding directly through them. So as written into my requirement is climate outreach, which is really something I would really enjoy to do. So that's what I'll be doing. A specific project, I don't know. Continuing to work on fire is definitely a possibility. They want people to do that, but I've been kind of given a blank check. They said you can work on like 5 or 6 different projects and choose one. So they have way more projects than people. So I definitely have a choice, which is nice to have.
That's a great position to be in.
Is there any other question? I don't think Brian never made it. Stalled for now. That's all right. He's already seen this in different forms.
Thanks for a great talk.
Yeah,
Thank you.